Our next speaker is going to talk about a workshop that occurred yesterday that was hosted by the Geology Club and the Department of Geological Sciences here at CSU Bakersfield. And I want to thank Dan Schwartz, who basically organized this organically as a means to really get into the weeds to talk about different issues related to carbon sequestration in the area. And Dan can't be with us today. He's in Champagne, France, so for obvious reasons he can't be here. But I do want to thank him for organizing this workshop. Our next speaker is Dr. Creties Jenkins, who is a geological engineer for Rose and Associates. And the title of his talk is The Subsurface Technical Issues Impacting Carbon Sequestration. And again, this is a report based on the highlights of what they discussed yesterday in the workshop. Creties.
My God, that's a bright light. Jeez. Well, good morning, everybody, and welcome to a talk about this workshop that we held yesterday. And I want to start by thanking, first of all, Tony and Cal State Bakersfield for hosting that workshop, and also the Pacific section of AAPG for sponsoring it, and the San Joaquin Valley Geological Society for the work that they did to encourage attendance and participate in the workshop yesterday. This workshop was to focus on subsurface technical issues, and the purpose, that was the purpose overall. And what we did first of all is identify some of the key issues that will influence the range of possible outcomes for these subsurface CO2 injection projects. And then focus on some of the key issues that have high impact, but also are potentially manageable by those who are operating those assets. And the key purpose of that, of course, is to mitigate the chance of future risks associated with that injection. And then we wanted to recommend some actions to address these, and that'll help us make better decisions regarding which projects to support and how to move them forward. In the workshop then, we had 15 participants, and you can see here that they include operating companies, research scientists, consultants, members of the local geological societies, and some grad students as well. So we had quite a diverse group that tackled these topics. And the issues that this group came up with are what you see here, beginning with the concerns about both natural seismicity, those of course are earthquakes we can't control, and induced seismicity, which might be micro-earthquakes that could be created by our operations. Faults and fractures, how do they compartmentalize the reservoir? Do they serve as conduits through which injected fluids could move outside of where they're supposed to be contained? What's the storage volume, and is it sufficient for us to have a project that has some commercial value? How much can we inject, and how fast can we inject those fluids? What the reservoir properties are that would allow them to accept and contain those fluids. How about the integrity of the new well bores we're going to drill, because we know that CO2 can be quite corrosive, and the integrity of those existing well bores, which were oil and gas producers potentially for decades. What happens when we inject CO2 into the ground? We like to do it in a supercritical state because it's much denser and we could store a whole lot more of it than if it's in the gaseous state. But that has to be at depths of greater than about 3,000 feet. So what happens if the CO2 finds its way to shallower depths than that? Are we able to contain and trap it? We'll talk more about that a little later. And also the characteristics of seals that would contain that injected CO2. Finally, then, we need to be able to monitor that CO2 plume to see if it stays where we intend it to, What is that confinement or containment area, and is it sufficient? And finally, what's the proximity to drinking water aquifers, and what's the chance that we might impact those at all? So these were the key issues, or I should say these are the issues that the group surfaced. And then what we did was we divided these into 4 groups, because we divided the 15 participants into 4 teams. And then we tackled the ones that you see here in more detail. Now, that doesn't mean we didn't address the other ones. Peripherally, we did. But these 4 areas have demanded our greatest attention. And so what we did then with each of these key issues is, first of all, we tried to assess what our current state of knowledge is about that issue, and then identify the gaps between our current state of knowledge and what needs to be understood in order to move these projects forward. And the reason, of course, we want to do that is to properly address the issue and reduce the chance of future risks that may come from these issues. And then finally, we propose some mitigating actions, that is data gathering and analysis, in order to close the gaps. So I won't go through all the slides that the teams came up with for each of these categories. But what I do want to do is just walk you through the next 4 slides, which summarize the actions as a result of this process. So we begin with natural and induced seismicity. So again, these are the things that we need to do to close the gaps between what we know now and what we need to know in order to have successful projects that include safe and affordable sequestration of CO2. So first of all, for natural and induced seismicity, we have to assess the historical seismic record, focus on the focal mechanisms for those earthquakes, quantify the subsurface stresses, orientations, and magnitudes, and conduct some fault slip studies to understand what faults might be critically stressed and have a tendency to move when we inject into the ground. We'll need instrumentation, both to form a baseline and then also as we inject for monitoring any sort of seismic activity. We'll want to conduct pre-injection monitoring, in particular to get baseline data. We'll need step rate tests to determine the fracture gradient to make sure that our injection pressure is well below that. And if we do induce some seismicity out there, what sort of ground motion could be created and how that might affect structures and such in the field. And then finally, we need to monitor that site, not just through the injection life, but afterwards as well, and develop some tools to help us better do that in the decades ahead. The second key issue that we focused on involves storage volumes, injectivity, and reservoir properties. And here's where we would start by conducting some well tests in order to confirm injectivity into the reservoir of interest and define what pressure we want to inject at and whether we have multiple compartments. And then determine whether that CO2 that we're going to put into the ground is going to have reactivity with existing rocks and fluids. And of course, quantify the salinity as well. We don't want to be injecting into something that could be a drinking water aquifer. We need to map the reservoir structure and understand the stratigraphy, essentially the architecture of the subsurface reservoir. Identify the reservoir rock types and their characteristics and how they might serve us in terms of being able to store those volumes. And then build some comprehensive fit-for-purpose models using the information we have. And that means high-resolution models to understand what might be happening in the pore space, and then much lower resolution models to understand what happens at the field scale, recognizing that models are very useful for understanding reservoir mechanisms and playing what-if games, but they become problematic for predictions unless you have some calibration. And so that's important to obtain through the early history of these projects and also looking at analogs. And obviously we want to try to develop some optionality here in case more wells or reservoirs are needed. The injection rates are low. If you have multiple compartments, you're going to need potentially extra reservoirs and extra wells as backup, and so we need to identify those to have that sort of optionality. Third key issue then we focused on was the integrity of existing well bores, particularly the legacy wells here. So we really need to do a thorough analysis of the existing well records and try to use some monitoring technologies to find the unknown and orphan wells that may not actually be in the records. And then develop some analysis tools to diagnose those abandoned wells with integrity issues. You don't want to wait until somebody cites dead vegetation around a wellhead to go out there and realize that you have a problem with a legacy well. And then, of course, if there are issues associated with these, we want to be able to go in and reseal those poorly abandoned well bores. We also need to think about the new well bores we're going to drill and have integrity testing of those. And if there's issues, have cost-effective remediation techniques we can apply. And also then look at analogous projects where CO2 has been injected into the ground. We have over 50 years of CO2 injection for EOR, for example, to understand the effects of CO2 and pressure on well metallurgy and the cement that is holding the casing in place. And then finally, then we had a group that talked about trapping, containment, seals, and offered some guidance. We need to begin by evaluating the trapping mechanisms for that CO2, both at a large scale, that would be structural and stratigraphic traps, and at a much smaller scale, the pore scale, where the mechanisms include residual, solubility, mineralization, and even buoyancy trapping. Then we need to assess the elements of the seal. Those three elements are capacity, integrity, and continuity. Capacity refers to the ability for that seal to not be breached by CO2 that would be pushing up through that seal, through the matrix of the seal. Seal integrity refers to obtaining information to understand whether there are faults or fractures that might breach that seal and form conduits into shallower formations. And then finally, seal continuity refers to that seal having sufficient thickness and lateral extent to serve as a seal over the large area that the CO2 plume will occupy. And then finally, again, we have analogs out there, particularly naturally occurring CO2 fields and injection projects that we can look at to give us some sense of whether those seals are going to be effective or not. And what's particularly helpful is if we could find places where we have multiple seals. If we look around the world at some of the successful projects, like the Quest project up in Alberta, they have 3 seals, and so that gives them some backup protection in case the first one ends up being breached. So that's could be an important element as well. So after we finish then talking about these key issues and sort of things we need to do to create additional confidence that these are going to be safe and successful projects, we talked about some of the disciplines and organizations that we would want to have involved in order to pursue these potential mitigation actions. And that would involve all the disciplines that you see over on the left-hand side there, and the organizations on the right-hand side, which would have personnel who could be dedicated to that sort of work. And that's not just industry, it's academia, including the research center that's going to be here at Cal State that could be providing that sort of guidance. The regulators, various consortia, oftentimes which are sponsored by organizations such as the Department of Energy. We have fantastic government science professionals who have been working carbon capture for decades now, and obviously they have a very key role to play in terms of their experience and understanding. And of course, we've got to communicate all of that to non-government organizations, the media, people who have a vested interest in seeing that what we're doing aligns with their desires as stakeholders to make sure that they're on board and comfortable with our intended actions. So with that, I'll thank you for spending a few minutes to hear what came out of that workshop, and I'd be glad to answer any questions you might have. So thank you.
We have time for a few questions. We've got one from the online audience.
Yes, the community is asking in regards of CO2 storage and earthquakes. If you could elaborate a little bit.
You know, I'm having a real difficult time understanding you, my friend. You may need to come up here to the front.
Oh, the question was in regards of CO2 sequestration and earthquakes.
Did you hear the question? Come up a little.
Yes, earthquakes.
It echoes back here a little
Oh, you
bit.
can hear me? Oh, sorry.
So is the question, what is the relationship between CO2 sequestration and earthquakes?
Yes, that's what the community is asking.
Well, how big of an earthquake do you want to talk about?
Small one, hopefully.
Okay, so Injection processes, which we've seen in many places, there's a lot of water that's injected in places like Oklahoma and Texas, and it does induce seismicity. These are microseisms, the vast majority of which are never felt by people. And if they are, then what happens is that regulators in those places will enforce some rules that require operators to inject lower volumes and at lower pressures so they don't continue to induce that sort of seismicity. But if we talk about the really big events, the ones that are scary, that could cause a lot of destruction, those are, in my view, unlikely to take place at the kinds of depths that we're talking about. Some of you may remember the Coalinga earthquake, for example, in 1983, where there was an earthquake, I think it was about a 6.5, but it nucleated at a depth of about 8 miles. And people looked at whether the withdrawals in the Coalinga field had anything to do with that. But those withdrawals are occurring at such a shallow depth that they had no impact on Mother Nature's desire to create an earthquake that was that large. So I think we need to separate those events that could potentially be tied to the sorts of operations that we're undertaking, and I think that those are small, and the chance of those, while certainly being possible, can be mitigated. The much larger earthquakes, I think we need to pause and think about whether we actually are going to have any sort of influence on those. It wouldn't seem historically that that's the case. I don't know if that answers your question or not, but okay. Got time for others?
One more.
Is this audible? Yeah. Are there reliable data that pertain to seismicity and surface mass balance that can be used by folks when they're planning a new sequestration site?
Is that clear to you, what he's asking?
Maybe I'll rephrase the question. In order to determine the impact of a new project on seismicity or on carbon mass balance, are there reliable data that have been collected by perhaps government agencies, perhaps other organizations, that can be utilized to form a baseline?
I'm certainly not the best person to answer that question, but I will say this: we've had withdrawal and injection operations in oil and gas fields for many, many years, and we can see the seismicity associated with those. And I think it's fair to say that as we start to inject CO2 in the ground, we could expect the same sorts of results, which again may result in some microseismicity but not large events. So we have that as a database, if you will. Plus we have readings that are taken from the seismic networks that we have in the state, and other people could respond about whether that information that's been collected provides a good baseline and therefore a way that we can measure the impact as we start to inject CO2 in the ground on that baseline, those baseline results. Again, not sure I answered your question very well, but okay.
Great.
What else?
Thank you.
Thank you.